That's what I said is I'm going to send an email. I sent it last night. Yeah, take it.
It's not what I wanted. Is it? Does it work?
So what you already know,
Find out.
what you want to do, and see if you fit into that category. And there's always opportunity for joining them.
I think that'll be okay.
Yeah, it's okay. So there's
Need some water. I'll be back.
so yeah. Are you? So are you on DevOps channel? Okay, you guys are on DevOps channel. Look at the log history of that channel. I think there was a discussion that doing a unit conflict to get the presentation. We were talking about it actually, and you could actually ask him because he has probably solved that problem. Put trigger. It's a lot of configuration. Right. Yes. But I'm asking about so you want to get all the logs on all your workers. I think it's a system. No, good. It's hard to answer, but you definitely reach the system. Yeah, but you send all your logs to one. It's for how much fancy? No, I mean something what are you posting on DevOps? I send you that to your I just email members. So everyone
would you mind if first I'll share my screen with my slide and then we will switch to you?
That's fine.
Because it would work.
Let's see.
So if I go here, I think I can overtake it. So I'm sharing my entire screen.
So am I still sharing? There we go.
yeah. Oh, because
All right.
Yeah, and then you'll share. You'll reshare once I'm done.
All right.
I promise it will be 2 minutes.
That's no rush. No rush. That's interesting that it's smaller. I wonder why.
I need to make it larger.
I could do this too. Let's see, center it a little bit.
I just need you can actually enlarge my slides.
Well, I'm just doing this scrolling bit. How's this? Is this? You think it's enough?
Depends when you talk to people. Yeah, that's
How's that?
funny enough, I was so uptight about the hiding all the while the first presentation of Scala School 9. So I made sure that my desktop is clean. There's no name of clients in there. All the CLIs whatever. And then in my bookmark.
Oh yeah. Right.
there is a current client that just stuck in there. Oh my god.
I know, it's hard.
It was
It's hard to catch everything, yeah.
yeah.
And I do that too. I look at when I see bookmarks, like, oh, what's a bookmark? Yeah.
So now yeah. Yeah, I'm better. Okay.
All right. So is Sean here?
He actually I kind of promised him to take a signature from you because he went to honeymoon. So he couldn't say no to circumstances. But he's miserable because he was so wanted to come. So you can have to promise to come again, you know.
Right, else, yeah. Kevin's got me. I actually that summer conference that you guys discussed
Okay, sounds good. I'll tell him that he didn't miss. He missed, but he didn't miss like in time.
not forever.
Yeah, exactly.
Are any of you guys going to be at ScalaToronto?
Yes.
I think I'm going to be at West Holidays too.
Yes, you are. I'm presenting in New England.
Okay, good. Did people ask you?
The last year I went to New York.
Okay. The Berlin venue is like in space. And it's
No, I've never been to Berlin. I've been to Frankfurt and Bielefeld. You know, I've been to Bielefeld, but I've never been to Berlin.
well, what I ended up doing is they have this museum island that's full of these amazing museums. Like they have that famous Cleopatra, who's Tut's mother or wife. Anyway, a bunch of famous Egyptian and Greek art. So I just spent the whole weekend up there walking around.
Maybe I should do it to enlarge.
Yeah, yeah. And it's just a cool town, and apparently, it's not very expensive, so it's become a startup.
Yeah, recently I see Twitter activity and Scout activity, people talking a lot from there, especially maybe on other Samsung what time was set up for this talk, maybe we start.
Whenever it's fine.
Yeah, I'll start.
Okay.
Yeah.
Hi everyone. I just wanted to let you know that we try to be on time and start on time, but apparently there is a construction going down, and there is several people who couldn't come in just yet, so we are just waiting for them to arrive. Another 5 minutes. Just please continue to socialize. Yeah.
Have a good day. Are you with a client right now?
Yeah.
Oh, yeah. So, do you want me to introduce me, or are you comfortable?
No, I'll do
So I'll be back there.
Yes,
Yeah. Okay. See you when I see you.
I made it in. You got time. Well, you were on the lane. Yeah. Well, Toronto is your first match. I used to be able to get used to that. It'd be like,
oh, this one. It was good by I
Did you guys?
Yeah, of course,
Exactly.
yes, once or twice. It was the first time. Yeah, I know. It was the first time. Which I don't mind. Yes. Actually,
There was another. Yeah.
Yeah, they are going to enforce. Yeah.
I thought it would make this easier to read your, there you go. Your hand. Hi everyone, once again, good evening. Welcome to Toronto Scala Meetup. Unfortunately, it's very hard to remember whether it's called Toronto Scala. Every time that I need to put a hashtag in my Twitter, I go and search which one exists. But you actually can use both. I'm saying all this because I'd like to ask from every one of you to make one tweet tonight. And the excuse that you don't have Twitter account doesn't help. Okay, open up one as we speak. Because even if
everyone will have only one tweet tonight. We will put New York to shame. It should be our goal. So anyways, Scala Toronto, probably you know what this meetup is because you came through it, but just as a refresher, we have a website, ScalaTorontoDeanWampler. It's pretty deserted now, we're trying to work on it. We have a meetup page, which is much more populated, so at least please be active there. We have Twitter account, ScalaTor was taken. We have also hashtag, as we said, and you also can be in touch with us, with Sean and myself. And my name is Katrine, who doesn't know, sorry for not introducing myself earlier. Now, what I could do next is actually to hijack this meeting because everyone here came for Dean and just continue to talk and talk. But I wouldn't do so, and I'll just, Kevin will be much better at introducing Dean than I am. So thank you for coming.
Yeah, thanks for coming in spite of the wonderful Toronto weather. So, Dean, you still have to come back. You know, I know it wasn't ideal. No, Dean's actually from Chicago. So a little bit about me. For those who haven't met me, I'm Kevin Weber. I work with Dean at Lightbend. I'm actually the only Canadian employee of Lightbend. So if you have any Lightbendy questions, get in touch with me. I'm in downtown Toronto. I just want to really thank Dean for coming out. So Drake's not the only person that's back-to-back. Dean has graciously agreed to do back-to-back talks last night at Spark and tonight at Scala. Just really awesome for that level of support for the Toronto Scala community. And I've been coming to these since 2013 or 2014. It's just awesome to see the amount of people that are here now. So I'll keep this quick. A few shameless plugs. I also run a meetup group called Reactive Toronto. A lot of Scala content there, but a little more in the context of architecture. And so we do things like we're going to do a microservices night, some hackathons on distributed computing, things like that. So if you haven't joined Reactive TO, give that a shot. And I also run for anybody that's really wanting to dive in deeper to anything you hear at this meetup. There's Scala Night School that Bold Radius and Katrin and their team run. And I've been going through with Don Kittle of Post Media, wherever Don is. Don's been hosting FP and Scala Book Club every Monday night. So we're going through Runar Ali's book, and I think we're up to what, chapter 6? Chapter 6. Yeah, so we might have to redo implementing streams by hand and using pure functional Scala. So if that's the kind of thing that interests you, come on out. So without further ado, Dean, if you've read anything about Scala before, maybe you've read his Scala book. He's also written a book on Hive. He's a member of our office of the CTO. We at Lightbend, we've started a big data team, and so we really like what we're offering is support for Spark developers. That there really isn't a clean cut separation for Spark developers that are getting into Scala maybe and looking at needing support. It's really sort of a cross concern, right? It's if you have challenges, we can help on the deep Scala knowledge, also the Spark, and Dean runs that team. And actually, if you file a support ticket, you'll probably hear from him once in a while. So thanks for coming out. This is going to be an architectural talk on what we call the fast data architecture at Lightbend. So Dean, thanks for coming out.
Can everyone hear me okay? Sounds like it. All right, give me a second to set up here. I'm gonna have to share my screen again. Entire screen, that's good. All right, I think we're okay. All right, how many of you were here last night? Well, you people are gluttons for punishment. I just don't know. Well, anyway, so last night I had pictures from the Olympic National Park in west of Seattle, 20 miles across the pond, so to speak, from Vancouver Island. I used to live out there, although this was a trip from last year. These are actually pictures from Colorado. They have almost nothing to do with the talk. but I just like to put in pictures in case you're bored with the content. And, you can do whatever. I normally have these on my website. I actually finished this 40 minutes ago, so I'll put these up later or post them to the meetups page. Somebody said I should tell you why we changed our name to Lightbend. Everyone in this room knows what the word typesafe means. When you talk to managers or business analysts, you get called typeface. That happened like the last day we were typesafe to one of our guys. He tweeted about this. So, but anyway, that was kind of the rationale, was just to pick a name that not that Lightbend really tells you what we do per se, but it sort of implies, that we're trying to change the world in some way. Ironically enough, we saw gravitational waves like a week before, so maybe there was something on the cards there. I don't know, but anyway. That's another interesting story if you followed that, but we won't tonight. But feel free to spam me on Twitter, or my email address is at the bottom, deanwampler@lightbend.com. And also, some of what I'm going to talk about is actually expanded in more detail in a white paper on our website. So if you don't mind giving your email address to marketing at Lightbend, and I'm going to do that all night. It's a drinking game, yeah. Someone's going to yell bingo when they fill in their bingo card with me saying typesafe. Anyway, you can go to this link to get that paper for more details. All right, let's start with a little motivation. Most of this is maybe familiar to many of you who are actually working in the real world, but what is fast data and why do we care? Well, it embodies a bunch of things, and one of them is e-commerce. So we have this term in the U.S., I don't know if you guys use it up here, but Cyber Monday. Black Friday is supposed to be the day after Thanksgiving when the brick and mortar stores break even for the year. That's where the term black comes from, although it can be pretty grim trying to compete with all of the desperate shoppers. And then Cyber Monday was when you're supposed to go online to buy stuff. Of course, it's BS. But anyway, Christmas time, a lot of times in the year, you'll get these spikes of traffic. Are you able to respond? You scale up, scale back down, and so forth. Netflix puts a new TV show that on. They do the whole season, and then people binge watch. So all of a sudden, you get these huge spikes of traffic. The Internet of Things is, one of these marketing buzzwords for a class of our industry, basically devices in the field. And it's not a new thing really, but it's getting a lot of attention recently. And there's some really interesting things going on in this space, like medical devices, switches, storage attached networks. They're all phoning home constantly. They're sending telemetry data if the owner allows it. And they're doing predictive analytics on this stuff to try to detect imminent failures so that they can actually service these things before they go wrong. Like an ultrasound machine. I actually worked on, not this particular one, but worked on ultrasound machines 20 years ago when I had less gray hair. And not that this made me have gray hair, but anyway. And we would do things like, that was pre-internet, so we didn't do quite this, but we always wanted to capture data about usability, like are they getting stuck in certain parts of the UI? Are they not using things like that. Aircraft engines, you hear this number, something like 2 terabytes of data is actually captured by each aircraft engine or emitted in terms of monitoring metrics and stuff, and most of it is thrown away. And there's obviously a lot of important data here. Some of that data did actually get sent over satellite, and we thought maybe we could find that Malaysian aircraft a few years ago, but we still haven't quite found it, although a big piece of wing turned up this past year. There's some interesting things going on here. So obviously, as you could imagine, all the UPS trucks, FedEx, whatever, are basically wired for GPS, so they know exactly where they're going, and they can do things like, are they breaking the laws? Are they, can we do better routing of deliveries? There's some amazing technology emerging in agriculture. They actually are tracking data for every single seed they plant, and they can track how much water has been received, how much soil or fertilizer, and if you think about it, this is a huge way to actually minimize the use of water, minimize the use of things that are, have side effects like pesticides by monitoring the performance of the plant and relative to the select shape of the slope, and then really very carefully on a per seed level deciding what you're going to do. Sensor networks. This is the picture of the global geoseismic network that looks for nuclear weapons, earthquakes, and stuff like that. Robotics is another class of problems now where, some of these things, these systems I've described, it's okay if they send up data later. Like an ultrasound machine doesn't need to be connected to the manufacturer all the time. Maybe you don't want that when it's in an ER or something. Robotics, obviously, if you're trying to do live video or live, human pilot, then obviously you do need real-time responsiveness, but then there needs to be some degree of autonomy like the Mars rovers. I heard a really interesting story from an engineer at Nest. They had a real problem as they started to grow where they would get these enormous packet spikes every morning around 7 a.m. when everybody got up and all of a sudden their thermostats were kicking in and raising the temperature. So they put in things like delays to kind of smooth out the size of those peaks. So lots of little problems with devices that have characteristics that are going to be globally true, not just individuals doing things. So this kind of has led us, and we could go on and on about examples, but we end up with a problem of systems that have to be able to interact with the world and exhibit certain qualities that are universally true no matter how they're implemented, whether it's our stuff in Scala or Node.js maybe, or anything like that. And there was sort of an industry consortium that got together, including people from Lightbend, to define, what are the sort of qualities that we think all systems should have. And this was kind of inspired by the Agile Manifesto, and it was called the Reactive Manifesto. Here's the first page if you want. That was a little fast. Let's go back. Obviously, I don't want to spend too much time on this, but just to describe what these 4 traits are all about, however you implement them. First of all, systems have to respond in a timely manner. This is not as trivial as it sounds, because when you think about it, there's no real difference between a system that's just extremely slow getting back to you and one that's dead. How do you know? So the idea here is that you'll always be able to respond to requests for service, even if it means that some of your responses might be, I can't provide service right now because the database is offline or it fell into the ocean or something. So it's the idea that there's something should be popping up here. We have to do this. Okay. We have to be able to really build in the notion of time into these systems so that we have predictable response times and we can meet quality of service requirements and not just allow the infinite tail, as it were. And it also means we have to actually treat degradation of service as just a normal occurrence that's inevitably going to happen, so that we have graceful ways of degrading the service we offer when it's not possible to provide the usual things. So time becomes a first-class concept in these systems. The next one is resiliency, and this is really about making errors first class, that we have to be able to recover from failure. So for example, failure should not be seen as disruptive, but actually routine. It's just something that happens all the time. I mentioned this last night with a Spark meetup. When you go to massive data centers like Google's, they don't even screw the hard drives in anymore. They have them duct taped in, or not duct taped. That'd be even worse. They have them like Velcroed in place, so that they can just, as soon as they fail, they just rip them out and throw a new one in. And they're just, the guys with massive biceps are doing this all day, basically. And then they go home and they do this all day. But, so failure is routine, so hence it has to be a first-class concept in these systems. They also need to be elastic, which means scaling up and down. And this is, once again, it sounds trivial to say it, but actually, how can you automate this? And how can you know when it's okay to bleed down the available nodes or instances of services? Somehow this has to be automated so that we can do this. And that means that we have to be smart about detecting the patterns that matter in whatever, I use the word inputs, but whatever that means, and then know how to do this automatically, because human intervention is a guaranteed source of failure. It also means eliminating things like bottlenecks and contention points. It means having something distributed over like lots of commodity servers and so forth. I have a great story actually. So my first internet company was in the mid-90s, and this was back in the era when you bought massive Sun servers. Like we had like two of them. We weren't big enough to have lots of them, but we had two massive servers. One of them, I think, was basically the database. This was like an e-commerce company. And the other one was just, serving websites. And the website engine was something called Broadvision that actually used server-side JavaScript at the time. Some of you are nodding your heads like, oh my God, you actually use that stuff. But anyway, we did. But we had an interesting problem with these things. Every now and then the CPUs would go nuts. And they would have to, and Sun was really like, they're ripping their hair out. They couldn't figure out why these really high-end CPU modules were failing and having to be replaced. I never found out why at the time, but like 10 years later, I read this blog post from James Gosling. He was the architect of Java. And he said what they discovered, somebody eventually had the idea of taking a Geiger counter into one of these servers and found that the little brackets that were holding the modules in place were like hot as a pistol. They were apparently made with radioactive metal. So they were basically nuking the CPUs. And so anyway, but it took Sun like 10 years, or not that long, but it took years to figure it out. But, if they had like mixed commodity servers, maybe that wouldn't have been such a big deal. Anyway, that was completely off topic, but it's a great story. Well, when I started writing software, we would typically have a main routine and we would just drive the world. Like maybe we would read files, we'd do some stuff and write things, but we didn't care what the rest of the world was doing. Well, obviously that's not going to work so well if you're providing services. So the core of all of these systems really has to be message-driven behavior. And the distinction between message and event would be a message is like a directed thing. I'm sending it to a receiver, whereas an event is something happened. So you might have a message that holds an event, but it's a more specific concept than event-driven. But it's sort of the same idea that I'm building a system that can respond to what's going on around the world. Okay, and just a little bit about this, and then we'll move on. So it's all about asynchronicity, no blocking, about just passing messages to trigger behavior. And it also has the nice benefit of providing a very clear boundary and a sense of abstraction and supporting the things that we all know we're supposed to do, like loose coupling and isolation of modules and so forth. So that's sort of the underpinning of what I think has to be true about fast data systems. And so what's fast data? Well, this is sort of one of those buzzwords, really, marketing buzzwords that people who try to make a living in software like to invent. All of you know about big data. Maybe many of you have lived that dream or suffered with it, I don't know. But really the key difference that this tries to encapsulate is that big data started out as really kind of a batch mode concept. Like, let's just get all the data in one place, across all of these silos in our organization. And then we can do like, global analytics over it, predictive modeling, whatever. But typically it's all sort of a batch mode thing. Maybe interactive if you have a tool like Hive and Hadoop where you can write SQL queries over the data set, but it's not in any sense modeling. Stuff is coming in from the outside world and I'm handling it right away without delay. Whereas that's just not competitive anymore. My favorite example of this actually is something that works just fine in a batch mode, and that's like indexing. Like if you're Google, I'm pretty sure they started out this way where they would just collect all this stuff with web crawlers, what was happening on the interwebs, and then they would index it with these periodic batch jobs. That is not competitive anymore because how many of you have like heard some news event happening and you immediately Googled for it to find information about it and hope that you hit a good website or like a news site. If the news sites are updating probably in real time, but if your search engine isn't finding those updates or at least reflecting them for hours, it's obviously really bad. So even things that can actually work as batch, we really want them to be as short as possible. The catchphrase I like to use is the gap between information or data arrival and information extraction should be as short as possible. Basically what I'm building up to is the tools that seem to be the most prominent emerging tools for this problem. The first one is Spark, which all of you have probably heard about. Spark is driving adoption of Scala like you wouldn't believe right now. I've had several meetings with potential clients and existing clients this week, and half of them have said that it was when they got Spark that they started using Scala for the first time. So if you've been like me, programming in Scala for years and really lamenting the fact that no one would let you use it, in your day job, well, you can thank Spark for at least driving like the masses to adopt Scala, and not just sort of the bleeding edge companies. But Spark is just a general purpose compute engine. Just to repeat a few points from last night for those of you that weren't here. It really gives you concise, elegant APIs that are essentially modeled after the Scala APIs, and I'll just show a quick example to show you what I mean. Now you could argue whether the Scala API, like the collections API, is truly functional. People love to argue about the Scala API, but I'll just make the claim that it is actually a functional API. But for data scientists, they like Python, they like R, and those are fully supported. And in some subsets of Spark, they actually perform as fast as Scala now. And there's even a Java API for people who really can't get a clue. Actually, it's amazing how many people just simply are not talking about Java at all. And, you know, like existing Java shops, and they're using Spark, and no one even mentions Java, except to say, we're having a hard time getting the Java guys to learn Scala. So, which, you know, I just sort of shake my head, yeah, I feel your pain. And you can even write SQL queries, which is pretty cool. Somebody told me recently that you know, they had a bunch of data analysts who were mostly used to SQL, and they just live in Spark SQL, writing SQL queries, because they already know SQL. It's not like a perfect, you know, ANSI 2003 compliant dialogue of SQL, but man, you can write a lot of queries and get a lot of work done without knowing any programming other than SQL. You can do exploratory analysis, which is, of course, something we all love about Scala. Through Python, R, SQL, you'll notice Java's not on this slide. And if you've ever worked with notebook metaphors. Now, most of us like developers, we're not really used to working in notebooks. We might be used to working in IDEs, but data scientists are used to working in things like IPython, or I think they call it Jupyter now. And I'm actually kind of trying to evangelize notebooks as a useful tool for Spark developer people to get used to using too, because it's a great way to prototype. If you think about working with the REPL in Scala, it's pretty nice, but there are things that are kind of a hassle about it. Like, what if you want to edit something that you just did and redo it, you know, tweak it and rerun it? It's awkward. You end up flipping back and forth to an editor or something, or maybe using a worksheet in Eclipse or IntelliJ. Well, it's very easy to do stuff like that in the notebooks. And if you want to like do things like graph the data, or maybe just list it in the table to see what you've got, really nice and easy to do that. So I encourage you to look at, my favorite is Spark Notebook, which is written in Scala and Play and stuff like that. And I want to talk about all the things you can do with Spark, but it does have a nice core that they've layered on top, different abstractions. And one of the major things they did is, because it's actually a batch mode processing system, which kind of doesn't fit the fast data model I'm trying to portray, but it is efficient enough that they came up with this hack where they could do mini batches. So you can specify in this streaming model a discretized streams where I'm going to do like every 5 seconds, I'm going to process the data that came in. And you're basically writing a batch job effectively that runs every 5 seconds over whatever data you just received. And if if the batch is wide enough, you can do things like machine learning. You can do incremental, so-called streaming, k-means, streaming logistic regressions. You can be training your machine learning models, making recommendations and so forth, in real time, quote unquote. But it's not low latency. We're talking seconds, not microseconds or milliseconds. So that's the key difference. And I'll come back to what you would do for low latency streaming in a minute. So it would look something like this. RDD is Resilient Distributed Data Set. That's basically their abstraction for a collection in batch mode. So you would have a fixed time window and a varying number of events coming in within that time window, and you would just capture each of those iterations into a RDD, and then you've got all the facilities of SQL queries, machine learning, as I mentioned, that you can run during each of those batch processing intervals. Actually, that's sort of a general trend. In fact, like streaming machine learning algorithms is kind of one of these growth areas right now, even outside of Spark. Pretty important. Well, I have to show some Scala in a Scala meetup, and this is obviously a high-level talk, but I did want to just give you a flavor for what this is. I went through this in more detail with the Spark group, but all the things, pretty much everything you see here should just like be obvious what's going on, because almost all the functions I'm using, with a few exceptions, are things that you're used to using with the Scala collections. You start with a Spark context. That's sort of your entry point. That's the thing that knows how to connect to your cluster or whatever you're using. That's this master argument. I don't really have a mouse here, but I can scroll in like so. And from that Spark context, you can load text files. You can load Hadoop files like Parquet, etc. If you use the SQL engine, it wraps this with some other stuff that we won't get into for time's sake. But then I can do things like, in this case, I'm doing inverted index, which is, I've just indexed the web. I've got a list of URLs and contents. I want to invert that into words, and then a list of URLs where those words were found. So this is like the Google killer I'm showing you here. So, you know, free business idea. Anyway, so the first thing I do basically is I split it on commas. I just assume it's comma separated data, and just the first comma, because obviously there might be commas in the text. Using a map step, return a two-element tuple. Once again, something you all know how to do if you're Scala developers. And then flat map, this is how I'm going to tokenize each of those lines into words. And what I'm actually spitting out at the end, if you look on the right here, I really could use a mouse. But anyway, notice that I'm spitting out two-element tuples, but the key, the first position, is actually a nested tuple. It's the word and then the ID that, you know, is the, whatever the URL is, how it was represented. And a seed count of 1. Reduced by key is actually nothing more than group by count. If you were writing this in SQL, that's what you'd write. But it's an optimized version of group by, because I really don't want all those groups. I just want to know how big they are, and that's all this does. The way it works is it basically gets together everything with the same key, which is, again, that nested tuple, word, and ID, and then it just uses this anonymous function for those ones to sum them up. So the output of this then will be unique pairs of words and locations, and then the count. And then I love to point out this line to Java developers. The next line is where I just shift parentheses. And you all know this, you pattern match, you can rip apart a deeply nested structure and then put it back together any way you want. You'd have to use, you know, like a Spring factory tuple-later, detuple-later, factory manager factory to do this in Java. So I really love this line. It's my favorite line in the program. And the great thing about it is, you know, when you have these functions in red and you know, in your toolbox, when you're used to writing stuff like this, then you just sit down and think, I need to do inverted index. How am I going to do this? Well, I can do it a step at a time, and then it just sort of flows out. And you kind of think, well, oh gosh, I need to move these parentheses, and you just write it and you're done. It's just amazing. So, you know, I'm not trying to brag when I say this, but it took me like 30 minutes to write the first version of this thing when I wrote it, because I just had all this stuff in my head, you know, what to do, and it just, like, you know, flowed right out without, you know, the Spring tuple-later factory manager factories. Okay, and then just to finish up, then you do a group by key. So I put word in the key position. Now I'm going to end up with a unique record for each word, and then a list of, you know, URLs and counts. And the last step is just to sort. I'd like to get the counts that are biggest first, because that's obviously the pages that reference this word a lot. So that's all the last step, the map values. Map values is a shorthand way of saying, instead of, I'm not changing the key, I just want to manipulate the value part of the two-element tuple. So it lets me just pass in the second part, which is the sequence of IDs and counts, and then I can just sort that. So this is something that's nice about Spark. Martin Odersky's actually done a conference talk where I think he even called it something like Spark, the ultimate Scala collections. And he says that for two reasons. Maybe there's more, but mainly two. One is that it actually really nicely extends the sort of core ideas that you see in the Scala collections to a distributed, theoretically unlimited scale context. But it also adds some pretty nice features that are both there for optimization as well as convenience. So like map values is convenient. Reduced by key is very important for optimization, you know, efficient group by. So anyway, that's the gist of it. Once again, you know, fits on a slide. That's always great when you can write a whole program that fits on a slide. But it really, I think, it brings back the joy to programming to be able to write stuff like this, especially compared to MapReduce. Okay, and just a little bit about performance, how this actually works. So actually, let me go back to this for a second. So each of these outer combinators, you know, map, flat map, reduced by key, map values, they were all returning a new RDD. these are immutable objects. That could be really inefficient, except it doesn't actually materialize everything. What it does is it pipelines together things that don't need to be shuffled back and forth. Like when I have everything partitioned over a cluster and I'm doing mapping and filtering and flat mapping, I don't need data from other partitions. So I can just ram all of those operations together, just run them together on each record, and then only materialize the last thing, which is the flat map. And the reason that had to be materialized is the next step was effectively like a group by, where now I need to shuffle key value pairs across the cluster to get all the common keys together and stuff like that. So this particular program breaks down into 3 so-called stages. The SQL data frame engine that's built on top of this stuff is actually doing dramatically faster optimizations. They're doing things like custom memory layout, cache-aware algorithms, things like that, to really optimize performance. But I won't get into those for time's sake. Instead, I want to talk about the other popular tools that are showing up in the big data, fast data ecosystem. There's really 3 basic tools that everyone is using now. There's Spark, Cassandra, and Kafka. Now you could substitute another database for Cassandra if you want. You could substitute Kinesis for Kafka or maybe some other message queue. But I'll talk about why Kafka is so popular in a second. How many of you have actually worked with Cassandra? How many of you have heard the word before? Probably most of you, yeah, okay. I don't want to explain Cassandra too much, but just to mention that it's one of these new SQL databases that emerged in response to the challenges of the internet, where you have your keys sharded over a cluster, a so-called ring, so that you get the redundancy, the failover, the resiliency of having a lot of nodes, as well as the scalability. And this is just illustrating that when a client connects to one of the nodes to make a request, let's say it's actually writing a new key value pair, then that will actually, the way it actually works typically is that will be stored on that node, and then as many copies as you've configured to write will be written to 3 other nodes, and there's a hashing algorithm involved in this, so that if any one of those failed, you'd still have all your data. And then we could go on and on about Cassandra. Of course, it's a key value store. It does have a SQL dialect now, which is kind of an interesting development. But it's really popular because it gives you a nice combination of flexibility of data structuring schema that you can layer on top of it if you want. It's also nicely integrated with Spark now, so that you can do queries over Cassandra tables using Spark. And that's about all I'll say. Now, let's talk about Kafka. So let me talk about this picture for a second. So I was backpacking with some friends, and we came across these sheep that were, there was actually a shepherd there, guy. He didn't look like the shepherds in the Bible, which really disappointed me. But no, he was just some guy on a horse. But anyway, I was looking for a picture from this trip to use for Kafka, and I have a picture of a river that I'll use later for Akka streams. But I thought, oh man, people put all kinds of stuff in Kafka. So all right, I'll just use sheep. Anyway, that's where that came from. What is Kafka? Well, it's an extremely highly scalable message queue system. LinkedIn wrote it, and they're now running something like 1.2 trillion events per day through Kafka in their own environment. So it's massively scalable. And it is really a classic message queue model where you have, one or more producers writing to a topic, and then of course you can have as many topics as you want. There's some other stuff I'm not showing about how these things are partitions, for resiliency and scalability. And then you can have as many consumers as you want who are reading through the topic queue at their leisure, so to speak. And there's a lot of things you can configure, like when these values will be removed from the topic and all this kind of stuff. They also describe it as like a log-oriented ingested system, because it really is kind of oriented towards the problem of, I just have all of these servers that are streaming massive log files at me. How am I going to ingest them all and then make them visible to the consumers? So they pretty much do everything. Well, I wouldn't say everything, but a lot of stuff is really oriented around this queuing model at LinkedIn. The other thing that's not as widely appreciated but is really important is that it solves this problem, which is, I could have these direct connections, n times m of them, between like sources of data and consumers of it on the right. This is obviously really bad for several reasons. The first one is it's a mess. It's hard to manage. It's hard to see what's going on. The other problem is, what if service 1 crashes? Well, now I've got all these like dangling pointers, if you will, of data that, what's going to happen to it? Does it just get dropped? Or maybe service 1 isn't crashing, but it's getting really heavily overutilized, and I want to split some of these streams to be processed by other services. It's really hard to do that when I have such a direct connection. But if I'm going through you can solve any problem in computer science with another level of indirection, right? Well, here we go. If I run everything through Kafka, then I've decoupled producer from consumer. It looks like a bottleneck, but as I just mentioned, this is an extremely scalable distributed system. So it really nicely decouples consumers from producers, and it lets me, mix and match how they work very nicely. So this is one of the most important benefits of Kafka, aside from its scalability. So actually a common pattern, I've talked about Spark streaming a little bit. Spark streaming, the mini batch model is somewhat complex, and it's actually not completely robust. There are ways you can crash it. So a very common pattern is, especially for data where I cannot go back and get it if I lose it, is to ingest it into Kafka and then read it out of Kafka into Spark streaming. So if the Spark stream drops it, or like if a node crashes, it can go back to the Kafka topics and reread the data. And you can actually pretty easily now get once and only once semantics with that structure. So I talked about Kafka, Spark, and Cassandra. The last little bit that's missing is, what about low latency streaming? Spark streaming is great for non-low latency cases where I want to do sophisticated analytics, but maybe what if I need to do like sub-second, like millisecond kind of resolution? Well, one of the sort of outgrowths of the reactive manifesto was the notion of reactive streams. And really, in a way, the names are almost coincidental because the concept is old and it's actually quite straightforward. But the idea is it solves a problem of consumers being overwhelmed by producers by setting up a feedback channel, out of band, where you can basically apply back pressure from the consumer back to the producer and adjust the rate of flow. So it's a flow control mechanism, and it's actually a very simple mechanism. The implementers of this standard have to decide how to do it. If you're doing it over a distributed network, you could use TCP back pressure, for example. But it solves these problems. So you have, well, going back to this for a second, a typical way to handle streams is to put a buffer in the middle so that, if there are transient rate, fluctuations in either the producer or consumer, it doesn't cause, hopefully, problems, that I have this buffer that's kind of growing in the middle. But if you run anything long enough, like months to years, then inevitably you're going to run into the extreme cases of, if I have an unbounded queue in the middle, I'll eventually have a situation where the consumer falls hopelessly behind and I fill up this buffer, meaning I fill up the heap and then it crashes. So that's not good. If I put in bounded queues, then I have another problem, which is, well, what do I do when the queue's full? I've got this little guy down in the middle. What's he supposed to do? What kind of decision should that little guy make when the buffer's full? Should it drop data? Should it try to save it to a file? It just doesn't have context to know. So the idea is that instead you use a bounded buffer but back pressure so that you never reach a point of data comes in and there's nothing you can do. So what would have to happen in this case is that normally you would have like a graph of these streams, and if one producer is being pushed back against, then it might be